Morning, everyone. I am very pleased to see all the students in the class. Even though I'm seeing you in online class, I'm very happy to see at the class. I hope that every student in the class are very safe from the COVID-19. Now, I'd like to shortly talk about the sequence of the class. In March and April, at the beginning of the class, we were talking about the importance of interconnection designs. Interconnection has three different categories, including signal line, power line, and ground lines. Usually, those subjects were neglected or were not covered in the conventional circuit design classes. After that, I was discussing the transmission line theory. Transmission line is a sphere where we can send high-speed distal, very broadband distal voltage and current wave with the speed of light. In order to do that, the transmission line structure has to have certain requirements. One of the most important requirements was that cross-sectional dimensions of the transmission line structure should be much smaller than the wavelength, so that at the cross-sectional structure, we can still define voltage and current. So that means we are neglecting the propagation and deflections at the cross-section. We are assuming that we have static voltage and current at the cross-section, and then these voltage and currents are traveling with the speed of light. And in order to control the waveforms, we have to control the reflections. One of the major mechanisms to control the reflection is to design the terminations. Sometimes we are putting the terminations at the source, or sometimes we are putting the terminations at the receiver side. Depending on the size of the terminations and the locations, we're gonna have different time delays, different waveforms, and different EMIs. Today, I'm going to talk about a little bit more about the termination schemes, and I'm going to extend my class to the single-end signaling scheme. As an example of study, I'm going to give you a special case of single-end termination that is called as SSTL. Usually SSTL is used between the I/O scheme between CPU and memory. The single-end signaling scheme has certain disadvantages. Sometimes, because our interconnections are very three-dimensional, sometimes we will see the impedance discontinuities. If we have impedance discontinuities, we will suffer reflections that sometimes, in most cases, those are not what we wanted. So in order to avoid impedance discontinuities at certain three-dimensional interconnections, we are designing a new signaling scheme that is called as differential signaling scheme. So next week's class on Monday and Wednesday, we are going to deeply go into the differential signaling scheme. So I would suggest students to attend the class next Monday and Wednesday. Those will be very important subjects. And this differential signaling scheme is usually used for PCI Express and USB or HDMI. Sometimes you want to send high-speed signal with more than 10 gigabps. A single-end signaling scheme may not be suitable because of the impedance mismatch and deflections. So in case of PCI Express is usually used for connection between computers, and USB is usually used between computer and external devices, and HDMI is usually used for connection between your computer or set-top box to the display. So these are very typical cases of a differential signaling scheme. And next week, we're gonna spend a talk in depth about the basic principles of differential signaling scheme. And a week after that, I'm going to talk about the crosstalk issues and inter-symbol interference and equalizers. And these 6 weeks or 7-week classes will be a set of lectures to cover the signal interconnection designs. After that, I'm going to move into the power supply design, especially for high-speed digital circuits. Now, I would like to move on a little bit more about the deflections and the time domain waveforms. Let me review again about this overdriven transmission line case, where receiving end is open termination. Usually this is an approximate case of small size CMOS input where we have very small input capacitance. But if we move on to higher and higher frequencies, this assumption will not be very effective. But in most cases, between the CPU and memory design, in most cases up to now, we can analyze timing waveform with an assumption of open termination. In an open termination case, we have reflection coefficient 1. At the receiver side, we are using 25 ohm source impedance. That means we are using very large driver size. A large driver size usually are causing a large amount of power switching current, and it will result in a large amount of simultaneous switching noise. So in this special case, I'm assuming that we are having very large driver size and turn-on impedance. I'm assuming that turn-on impedance is 25 ohm. And first, and also flight time from source to load is being assumed to be 250 picosecond. And I'm assuming that the transmission line impedance will be the 50 ohm. When we are applying 2 volt, we are assuming that source voltage is 2 volt and we switched on the transistor, then suddenly we will generate a voltage step at the source side, and it will be propagating along the transmission line. And this step voltage will reaches to the load side because of the deflection coefficient 1, 100% of this step voltage will be reflected. And then if this reflected voltage reaches to source end, because the source impedance is 25 ohm, that is smaller than 50 ohm, we're gonna see the reflection coefficient that is going to be 0. So it's going to be negative number. So because of positive reflection coefficient at one end and negative reflection coefficient at the other end, we're gonna see the ripples and periodic up and down, and it can cause an EMI issue. Now let's spend a little bit of time to calculate this voltage wave generations and deflections. Incident voltage step is determined by source voltage multiplied by impedance ratio. And because the source impedance is 25 ohm and transmission line is 50 ohm and transmission line is 50 ohm, by the relationship between the impedance of source impedance and transmission line impedance, we will see that 1.55 voltage step will be generated and will be propagating along the transmission line. It is larger than 1.0, that is because we are having large transmission line impedance and smaller drivers, a smaller source impedance. So because of the smaller impedance and larger driver size, we was able to make a large amount of step voltage. And then let's calculate the source reflection coefficient. And that is controlled by this equation, reflection coefficient equation. Source impedance is 25 ohm and transmission line is 50 ohm. Source impedance 25 ohm, transmission line is 50 ohm. That means 33% of the wave will be deflected, minus 0.333. And of course, source load reflection coefficient 1. By having this incident voltage wave and source reflection coefficient and load reflection coefficient with the flight time, we can draw the voltage waveforms at the source and load. In order to do that, we can use multiple reflection timing diagram. And initially, we are generating 1.33 volts. That is determined by the relationship between source impedance and transmission line impedance. And this 1.33 voltage step will be totally 100% deflected at the load because of open termination. And this 1.33 volt will be added to the initial voltage step. So this 1.33 and 1.33, at the initial state, this step voltage will propagate from source to load, but this reflected voltage wave, even though its amplitude is 1.33 volt, it will be deflected into the back direction. And then 30% of this 1.33 volt will be deflected, and this actually, this is negative step voltage will be reflected to the G direction, and 100% of them, negative transition will propagate into minus direction. We have two different directions, upper transition or negative transition, or G direction propagation or minus G propagation. So at this time, if we look at the source, from the time 0 picosecond to 500 picosecond, that is 2 TF, the voltage will be the 1.33 volt that will be determined by this incident voltage. But once this reflected voltage waveform arrives at the source, we have to add this reflected voltage and another reflected voltage. So from 500 picosecond to 1000 picosecond, we have to add initial voltage step and reflected voltage. Actually propagating in the G direction. This is minus G direction. This is another negative step, but propagating in G direction. All this has to be added together, and that is becoming 2.2 volt. So because of multiple reflections and multiple reflections, at each time interval, we can calculate the total voltages. By having those analysis, so initially at the source, initially from 0 to 500 picosecond, it was 1.33 volts. From 500 to 1000 picosecond, reflected voltages will be added together to become 2.2 volts. So battery itself is 2 volts, but at certain period, it is more than 2.2 volts. In the circuit theory, if you look at this as a circuit, because source voltage is 2 volts, it is impossible to have more than 2 volts because of this circuit open terminations and source impedance, whatever. All these voltage levels in each circuit cannot exceed 2 volts. But in the transmission line theory, because of multiple reflections, it will have certain time interval where it is more than 2 volts. Without understanding of multiple reflections, especially in open termination, the reflection coefficient is becoming twice, and sometimes it is becoming higher than 2 volts. That is very interesting thing. And if you analyze all this time domain waveform, we're gonna have certain period and certain period, it is going higher and lower repeatedly. As I mentioned, that it is because of the reflection of some positive number at the load side and deflection at the minus reflection coefficient at the receiver side. So this is an example where we can analyze the waveforms, distal, high-speed distal waveforms with the principle of excitations and multiple reflections. Once again, I would like to say that by controlling source impedance and termination impedance and length of interconnection with the characteristic impedance, we will have different type of source and receiver voltage waveforms. Initially, when you are designing interconnections, you have to do this kind of analysis. You can do it with the pencils as I am demonstrating right now, or you can use it computer simulations. I know that Ujin or Jang Ujin or Jongwoo may be staying there in the class. I'm going to ask some questions at the end of this slide. Let's take a look at a case where we have source impedance 75 ohm and termination is open termination. That means load reflection coefficient is 1 and source reflection coefficient is larger than 0. So all at the end of reflections, we're gonna add more voltages because of positive voltage coefficient. And if you look at the timing waveform at the source, initially it's gonna have 0.8 volts that will be determined by source voltage and source impedance and the transmission line impedance. In this case, source impedance is large, then means the driver size is small. That is why we initially have 0.8 volts. And we're gonna have reflection coefficient at the receiver side. Because of this reflection coefficient 1, we're gonna have another 0.8 volts. And also we're gonna have positive reflection coefficient. We're gonna have another addition of that. Because of that, we're gonna have 1.7 volt after twice of flight time. After another twice of flight time, we're gonna have positive step and it will go closer and closer to 2 volts. 2 volts is the initial condition of circuit operation of the circuit. Please remember that this analysis is assuming that based on the assumption that rising time is much smaller than the flight time. Of course, assumption could be rising time is 1 picosecond, and here flight time is 250 picosecond. So this is a case where we have really high-speed driving circuit. But let's assume a case where rising time is maybe 50 picosecond. So rather than having very steep rising time, we're gonna have little bit of slow rising time. So actual waveform will have little bit smooth rising time. And again, we're gonna have a smooth rising time. But still, this smooth, even though it is a smoothing rising time like 50 picosecond, but still that is much smaller than 200 picosecond. So we can consider the multiple reflections, and we can still apply the transmission line theory. But let's think about a case where we have 600 picosecond rising time, very slow digital signal. Then it will not see any reflection effect. It is very slow signal, so it has no chance to see any reflection effects or transmission line effect. So it is gonna be something like that. And then it's gonna be more likely RC type circuit behavior. And this rising time is gonna be determined by RC time constant of circuit. So what I'm saying at this moment is that if your rising time is very fast, this is actually very high frequency signal, then we can apply the transmission line effects, and we're gonna see all these multiple reflections. But if your rising time is very slow, it is the area of circuit theory, and it is gonna go behave as if it is a RC circuit. So depending on the rising time, it's a case of very high-speed digital signal, we have to apply the transmission line theory. But if your rising time is very slow, then it is an area of circuit theory. But eventually, after certain time delay, it will be the same. That is one thing I would like to talk to you today at this moment. 우진, 장우진, no, 장우진, are you there?
예, 교수님.
네, 만나서 반갑습니다. 약간 요 페이지 한번 제가 얘기하고자 한 바가 있었는데 조금 영어는 서툴지만 했는데 한번 설명해 주시겠습니까?
예, 지금까지는 저희가 라이징 타임이 1피코세컨드 정도의 굉장히 고속 디지털 신호를 이제 보낼 때
네.
그 속도를 기준으로 이제 분석을 이제 했었는데, 이제 라이징 타임이 실제로 1피코세컨드가 아니라 이제 플라잉 타임보다 좀 느린 시그널로
네.
이제 신호가 인가될 때는 기존에는 이제 멀티플 리플렉션 등의 어떤 트랜스미션 라인 티어리가 적용이 됐는데, 이제 라이징 타임이 플라잉 타임보다 느린 경우에는 그런 트랜스미션 라인 티어리보다는 이제 서킷 티어리가 적용이 돼서 이제 라이징 타임이 멀티플 리플렉션처럼 올라가기보다는 일반적인 RC 컨스턴트의 그러니까 RC 딜레이가 생긴다는 것으로 이제 이해를 했습니다.
네, 맞습니다. 아주 훌륭하십니다. 저보다 훨씬 훌륭하시네. 설명을 잘하시고. 그래서 이게 트랜스미션 라인과 서킷 티어리가 분리된 게 아니라 다 맥스웰 이퀘이션에서 온 건데, 특정 조건에서는 트랜스미션 라인 이펙트가 도미넌트하고 특정 조건에서는 이제 회로가 도미넌트한데, 트랜스미션 라인을 티어리를 쓴다는 건 라이징 타임이 굉장히 짧은 경우인데, 길이에 비해서 그 경우는 명확하게 보이지만 점점점 높이면 서킷에서 우리가 봤던 회로 파형으로 이렇게 수렴해 간다, 이렇게 봐지겠습니다. 지금 이제 라이징 타임과 플라이 타임을 비교했는데, 플라이 타임이 또 짧아지면 트랜스미션 라인 길이가 1마이크론, 10마이크론이 되면 플라이 타임이 10피코세컨드, 1피코세컨드 되거든요. 그러면 그런 또 익스트림리 짧은 케이스는 트랜스미션 라인을 또 적용할 필요가 없는 경우죠. 트랜스미션 라인 해석해서 또 되긴 되지만 그렇겠습니다. 그러니까 서킷처럼 이렇게 멀티플 리플렉션 보이지 않게 하려면 또 라인을 짧게 하는 그래서 이제 퓨처 인터커넥션은 짧아질 수밖에 없는 그런 게 있겠습니다. 장우진 학생은 어떤 전공이신가요?
다시 한번 말씀해
예,
주시겠습니까?
우진이는 전공이 어느 쪽 분야예요?
저는 저희 아날로그 집착회로 설계 쪽이고요. 상세
네.
회로는 이제 데이터 컨버터랑 베이스밴드 회로라고 봐주시면 될 것 같습니다.
네, 이런 트랜스미션 라인 티어리를 거기 그쪽 아날로그 회로 설계할 때는 파워 그라운드 설계가 더 중요하지는 하겠지만은, 뭐, 트랜스미션 라인 티어리를 바로 적용하는 경우는 많지는 않을 것 같지만, 이렇게 시야를 넓히는 계기가 됐으면 좋겠습니다.
예, 감사합니다.
네. Now, I'd like to continue my discussions of transmission line theory with the termination effects. Now, I would like to discuss a special case where we have large loading. Assuming in the previous case, I was saying that I'm assuming that loading capacitance is extremely small. But in order to give you more understanding of this transmission line theory, I'm going to consider a case where we have very large capacitance. Usually capacitance is good for power and ground because capacitor is a big tank of charge. So that means we can send very large amount of charges and we can store them for power supply and ground return path. And usually capacitance is good for a filtering purpose as well. So we can minimize the power supply noise or ground noise. Those are good for usually power and ground design. But large capacitance is usually, I'm not sure it is good or bad for signaling design, but especially for high-speed digital signaling, CAL may not be a good element or plastic element in high-speed digital signaling. That's why I'm going to talk a little bit about that at this moment. If we have a large capacitance at the load, that means at the high frequencies, it is becoming very low impedance. At high frequency, impedance will be very small. That means deflection coefficient is becoming almost -1. Even though there is no DC current path because of this is capacitance, we're gonna see large deflection coefficient. Especially for power design, sometimes we are putting capacitor. That is being called as decoupling capacitors. And because of decoupling capacitor as low impedance, we're gonna see large amount of deflections. That is causing huge amount of simultaneous switching noise. So that is going to be a very difficult subject, which will be covered later in our class in May or June. As I mentioned many times, signaling, the level of difficulty of signaling design is 1, but power design is maybe level 3, and ground level maybe level 10. So that is because of the deflection coefficient of -1 of capacitance. But let's forget about the power ground at this moment. So we're gonna have deflection coefficient -1 almost at the high frequencies. But at the DC level, it is open termination, but the high frequency, it is very negative deflections. And also, I'm assuming that we are not, we have 50 ohm source impedance. That means there will be no deflections at the source. So after twice of time flight, it's gonna be a DC state or circuit state. So because of that, I'm saying that from 0 to 2 flight, it is gonna be a wave behavior will be dominant. But after twice of flight, RC circuit response will be dominant. Who is controlling 2TF? the source impedance is controlling 2TF. Because of the source impedance reflection coefficient is 0, after round trip, we are not going to have any more reflections. Now, let's take a look at the voltage waveform at the receiver. The voltage step voltage, 1 volt will propagate from source to receiver, but once it arrives at the load, suddenly reflection coefficient is -1. So initially voltage was 0, but somehow once this step voltage, 1 volt is arriving there, it want to go up. But suddenly, because of this capacitance, it will reach the minus reflection coefficient and it is going back to the 0 volt. So we're going to have small ripple there. If this is the ideal source open termination, we are not going to see any this ripple. But because of some time delay associated with the capacitance, we're going to have some pulse. But eventually it will go down. Then it will reach to the source and there will be no reflections. Once this reflected voltage is arriving at the source because of this impedance matching and -1 reflection coefficient, initially it has source has 1 volt step, but after round trip it will go down to 0 volt. That is the initial condition of these open terminations. From there, all this source voltage and load voltage will be the same phase because we are not going to any propagation effect between source and load. It will go to the type of circuit type of voltage waveform, and that is the RC type of circuit. And this RC type of time delay will be controlled by the source impedance 50 ohm plus twice. Of course, we have the twice of flight time. That is the first component. Second component is this loading capacitance and the transmission line capacitance multiplied by source impedance. So one observation here is that because of capacitance, we are going to have some negative dip. And eventually it will go to the 2 volt, that is the DC condition of this circuit. So this is another example of mixture of wave properties and wave behaviors with the RC type circuit response. So Jongwoo, I saw your name on the Zoom. Are you there? Jongwoo, okay. Would you speak a little bit loud?
네, 교수님.
네, 한번 설명해 주시겠습니까?
네. 로드단에 이제 큰 캐패시턴스가 달려 있고 이제 소스 임피던스를 트랜스미션 라인 임피던스가 맞춰줬을 때 이제 소스단에서는 이제 반사 개수가 0이고 이제 하이 프리퀀시에서 그 로드단에서는 반사 개수가 -1이 되는데 이제 이때 그 2볼트를 줬기 때문에 소스에서 타임 플라이가 지나면 이제 1볼트가 로드단에 전달이 되고 이게 다시 반사가 돼서 이런 그 이 타임 플라이 이후에는 그 소스단에서 이런 펄스가 형성이 되고 구형파와 같은 이런 펄스가 형성이 되고 그리고 로드단에서는 그 전압이 이제 도착을 하자마자 바로 반사가 되기 때문에 이제 아주 작은 이제 펄스가 형성이 되는데
네.
이 이후에는 이제 RC 서킷이 돼서 그림과 같이 이제 이렇게 RC 서킷의 특성에 따라서 증가를 하는 이러한 형태를 보이게 됩니다.
네, 네. 사실은 이거 설명하기 되게 어려운 건데 너무 잘하시네요. 우리 학생들은 다 천재인 것 같아요. 진짜로. 진짜로. 자, 그래서 또 한 번 강조를 하면 이 시간이라는 쪽에서 한번 들여다 보니까 전파 현상의 텀하고 RC 타임 현상이 두 개가 더해지더라. 네, 그런 게 하나가 있고 파형도 웨이브 현상이 보이는 파형과 회로적인 파형이 보이더라. 뭐 그런 현상을 가지고 한번 캐패시터 가지고 이렇게 한번 설명했고요. usually 그 캐패시턴스는 임피던스가 낮기 때문에 반사계수가 마이너스가 돼서 파형을 이렇게 마이너스로 이렇게 한 번씩 떨어뜨리는 그런 게 됩니다. 예. 감사해요. 나종우 학생은 어떤 전공이신가요?
저는 디지털 외부 쪽을 전공하고 있습니다.
네, 네. 그러니까 이런 현상까지 보려면 진짜 하이스피드 디지털이었는데 해야 되는데 앞으로 뭐 IO 데이터가 10기가 이상 가면 10기가 bps 이상 가면 온칩에서도 이런 거를 한 번씩 들여다 봐야 되지 않나. 이런 거 무시하고 회로 시뮬레이션하고 디자인하면 가끔 이런 무시했던 현상들 때문에 조금 오동작하고 그럴 수도 있겠습니다. Now, I'd like to move on to another case where I have an inductor in series with differential line. In this case of special case, I designed this termination with the source impedance is 50 ohm. That means we are not going to have any reflection. That means source reflection coefficient is 1. And another assumption I'm having here is that this transmission line length is infinite. So I'm not going to consider reflection effects. Or we have 50 ohm terminations, then we will neglect the reflections. And we have two sections of transmission line, number 1 section and number 2 section. In the number 1 section, we have time flight L, time and transmission line impedance. In the section of 2, we have another transmission line with the impedance G0. But when we are connecting this transmission line section 1 and section 2, I'm assuming that we have very large inductance. Usually this inductance is coming from package or via wire or traces. You remember that if we have a transmission line, we have a ground plane and signal line, we have a height h. If h is becoming very large, then we are going to have large magnetic field. Then we're gonna have large inductance. For example, if you have a package wire, ground is very located very large distance, that means H may be very high. Then this kind of interconnection, who has very higher thickness between your signal and ground, it has series inductive element is very significant. So in many cases, even though you have very small inductance, if your signal transition rising time is very fast, you have to consider this inductive effect. So at this moment, I would like to spend some time to discuss about the effect of this inductance. If we are having 2 volt and the transistor is turned on with the source impedance 50 ohm, we're gonna generate 1 volt step pulse. And because of this large inductance, when this step pulse is reaching to this discontinuities at here, we're gonna have reflection coefficient is 1 because this inductance is looking at as a very high impedance. In the previous slide, with a very fast switching time, capacitance is behaving as a short circuit, but inductance is becoming as an open circuit at a very fast transition time. Because of that, we're gonna have huge deflections. And this reflection will go back to this source. And because of that, it will go to another 1 volt. And it is going to go to a 2 volt. That is a condition for open termination. And from that point, this line is 2 volt, and we have 50 ohm, and we have inductance. So it will decay as an exponential behavior. And this decay time will be controlled by the flight time and the LR time constant. And that is the one meaning of this analysis. First meaning of analysis is that we have 2 components of time delay. First one is the wave property, and second is the circuit property. Second observation I would like to emphasizing at this moment is that when we have inductance, we're gonna have positive pulse. When we have capacitance, we usually have negative pulse because of negative reflection coefficient. And sometimes we have positive reflection coefficient because of this inductive discontinuity. Because inductor has large impedance and it is causing a large reflection coefficient. 박가영, are you there? She may be not there. 이상욱, are you there? Maybe not. 윤지원 from Electrical Engineering Department, are you there?
네,
네, 한번 설명해 줘 보시겠습니까?
앞선 상황과 다르게 이제 굉장히 빠른 트랜지션, 그러니까 짧은 트랜지션 타임 상황에서는 이제 캐패시턴스는 굉장히 낮은 임피던스, 숏서킷으로 고려를 할 수 있는데, 이제 이 예시 같은 경우는 인덕턴스 같은 경우는 반대로 굉장히 하이 임피던스로 고려를 할 수가 있기 때문에 이제 리플렉션 코에피션트가 마이너스 1이 아닌 이제 1로 해석을 하게 되면 다음과 같이 포지티브한 펄스, 그러니까 반사 펄스가 나오게 되고, 그래서 2TF 이후에는
LC
회로로 고려를 할 수가 있어서 다음과 같이 이제 DC 컨디션으로 수렴하는 파형을 관찰할 수가 있습니다.
네, 그래서 우리가 비티스타럴 서킷을 이제 파워와 그라운드 나중에 하겠지만 하여튼 이상한 파형이 많이 잡혀요. 그런데 그런 경우가 많은 경우가 이렇게 멀티플 리플렉션에서 생기는 거라서, 가령 여기서 이제 스텝 볼티지가 인풋이 2볼트인데 회로적으로 보면 오실로스코프로 찍었을 때 2볼트보다 높은 파형이 있을 수가 없는데 실제로 오실로스코프로 찍어보면 이상한 파형이 나오고 플러스도 되고 마이너스도 되고 이러는데, 이런 게 다 리플렉션에서 오고요. 이런 현상을 또 관측하기 어려운 게, 오실로스코프를 보기 위해서 프로브를 찍어야 되는데 그 프로브가 또 파라시틱 캐패시턴스가 있어요. 그래갖고 본질을 우리가 볼 수가 없어요. 이런 현상들은 그런 게 또 어려운데, 이제 시뮬레이션 상에서는 볼 수가 있죠. 시뮬레이션 상에 볼 수가 있는데 해석하기가 되게 어려운데, 그 해석하는 하나하나 조각을 지금 제가 해보고 있습니다. 땡큐, 고맙습니다. So this is a little bit summary of the previous 2 slides. So if you have some parasitic capacitance in your transmission line, so we are assuming that in your transmission line, we are assuming that we have totally this structure. But sometimes we are having some physical element, wire or pad, or sometimes if you have metal structure here, you're gonna have parasitic capacitance. There could be many cases of 3D interconnection who has parasitic capacitive element. Then if you are measuring or simulating the waveform, you're gonna have this kind of dip. Sometimes you have transmission line 50 ohm, sometimes if you have transmission line 50 ohm, 20 ohm, 50 ohm, then you're gonna have this kind of dip because of multiple reflections at here. And of course, if let's assume that you have 50 ohm transmission line, but if you have very wide W, then you usually have very small impedance, then you're gonna have this kind of case. However, if you have a case where you have very inductive element, usually you're gonna see this higher ripples. And this kind of thing can happen that when you have transmission line who has very higher thickness compared to 50 ohm, this can cause very characteristic impedance smaller than 50 ohm. Then you're gonna observe this kind of positive pulse while you are sending high-speed digital signal. Sometimes you have C and L together. In many interconnections, L component and C components are coupled together. Then you're gonna see this kind of ripple, and this ripple resonance may be coming from LC type of resonances, and it may cause the EMI and jitter issues. Usually this kind of LC parasitic element is coming from package connector or via. These kind of structures are needed for transition from one interconnection structures to another, from PCB level interconnection to on-chip level interconnection, or on-chip level interconnection to cable type interconnection. So when you have transitions from one level of interconnections to other, you're gonna have this kind of ripples. And in order to avoid this kind of ripple, you have to minimize capacitance and inductance. Sometimes, if you have transmission line G0 and transmission line G0, sometimes you're gonna have some planes. In the PCB, you have power plane and ground plane. If you are sending some signals through that power and ground via, you will feel the plastics of this power and ground plane. If you have this power and ground plane, you're gonna have incident wave and reflected wave, and incident wave and reflected wave in X direction and Y direction. In transmission line case, we only consider incident and reflections at the G directions, but in the power and ground planes, in the PCB, the difficulty is that you have X direction incident and reflections and Y direction incident reflections, and all these end are open terminations. And because power and ground cannot be connected together, if you connect power and ground, that it is gonna become a short circuit. We cannot accept that because power and ground plane have separate voltage. We don't wanna have any current path between power and ground. So it will cause a lot of multiple reflections, and it is going to cause this kind of ringings, and it is causing the EMI and jitter and issues as well. So ideally, we want to send stiff, very fast, clean digital signals and rising time and falling time because of this kind of things, and we're gonna have this kind of ringings. And those are some typical part of the high-speed digital design. In order to avoid this kind of ringing may coming from reflections, and as we said, multiple reflections and parasitics, and plane resonances. And those are actual problem, and a lot of cases over 10 gigabps, and these are the really the engineering issues. In order to understand, you have to understand packaging connector via as well as the PCB. That is the difficult part of engineering. Hyunwoo, are you there?
Yes.
Would you summarize this slide for me?
고속 스피드에서는 항상 여러 개의 라인이 있고, 그 라인 길이에 따라서 인덕턴스가 생기고, 그래도 그 라인 간에 디스턴스 커플링이 생기게 되는데, 그때마다 이제 고속 주파수에서는 인덕턴스에서는 오픈 서킷처럼 작동을 하고, 캐패시턴스는 이제 스페이스랑 작용을 해서 각각의 리플렉션 코에피션트가 양수값, 음수값을 가지게 돼서 그 사이 상호작용을 하면서 원래 일정해야 될 것 같은 볼티지 전압이 링을 이렇게 돼서 불안정하다고 이해했습니다.
네, 마이크 약간 좀 안 들렸는데도요. 하여튼 설명 감사하고요. 자, 그래서 아이디얼한 트랜스미션 라인은 해석도 좋고 예뻐 보이는데 멋있어 보이는데 실제로는 아이디얼에서 조금씩 벗어난다. 그래서 인터커넥션과 인터커넥션이 연결되는 그 주는 중간에 파라스틱 구조, 특히 3차원적인 구조, 대표적인 게 비아, 뭐 와이어, 뭐 트레이스 이런 게 있는데 이런 게 이제 L과 C를 갖게 됨으로써 이제 캐패시턴스는 밑으로 튀게 하고 인덕턴스는 위로 튀게 하고 이러면서 링이 일어난다. 그래서 깨끗한 파형을 되게 어리기가 어렵다. 이게 아까 요 지금 왔다 갔다 하는 게 여기서는 LC 관계에 의해서 생겼지만 앞에 슬라이드에서는 라인의 길이와 반사에 의해서 생겼잖아요. 그죠? 두 종류가 있는 거죠. 아주 하이 스피드에서는 트랜스미션 라인 멀티플 반사에서 생기고 또 어느 인터커넥션 구간에서는 LC 레조넌스가 만들고요. 또 어느 구간에는 이렇게 PCB에서는 시그널이 잘못 지나가다 보면 파워와 그라운드 플레인을 만나는데 이때는 플레인 안에서 막 전자파 현상, 캐버티 현상이 생기는 거예요. 그 현상 때문에 또 링잉이 이렇게 생깁니다. 그래서 회로 이론을 볼 때도 있고 트랜스미션 라인 볼 때도 있고 또 이렇게 3차원 전자파 해석까지도 해야 되는 이런 안테나 이론까지도 해야 되는 이런 영역이 있겠습니다. Yeah, so far I was talking about the multiple reflections and all the parasitic and resonance effects. Now I would like to move on to single-end transmission line scheme. I would like to give you an example which is named as series terminated logic, SSTL logic. Usually, as I know, this is used for DRAM interface with the CPU. We have many different types of SSTL logic. In this case, I think I'm going to talk about this case. Initially, SSTL3 is the 3.3 volt system. Now, in this case, for an example of study, I'm going to talk about 2.5 voltage system. Right now, in the case of DDR3, we are using 1.5 volts. And this is my imagination, probably right now, companies are developing DDR4 or 5 or 6, probably power supply may be around 1 volt or something like that. One of the reasons that we are reducing this voltage level from 3.3 volt to 1 volt is reducing the power consumption, and especially I/O power consumption, because we are communicating more between DRAM to CPU and GPU in AI computers, and we are spending more and more power in the I/O. Traditionally, I/O power consumption occurs mostly in the cores. Who is doing all these digital calculations. But as I know, more and more power consumption is happening at I/O circuit. One of the obvious solutions to reduce the power consumption is to reduce the VDDQ. Of course, power consumption in circuit theory is half CV square. So one of the most dominant way to control the power consumption is to reducing the power. Next one is to reduce capacitance, I/O capacitance. one possible way to do that is to make a short interconnection between CPU and GPU to the memories. That's why I'm thinking about 3D stacking structure between the CPU, GPU, and memory. That is the way we can reduce the power consumption. In this special case for study, I'm going to talk about a case of 2.5 volts. In this special case, termination is attached to the power. VTT, that is the half voltage of 2.5 volt. That means inside your chip, you need the power supply of 2.5 volt as well as 1.25. Also, you're gonna have to have a very stable voltage of V reference. At the receiver side, they are comparing this received signal with the reference voltage. If that received voltage is higher than 1.25, it is logic level becoming 1. If the received voltage at VB is lower than 1.5 volt, receiver will see that as a digital logic level low. But one interesting thing is that compared to previous study, this termination is attached where 50 ohm is attached to power supply. This means that when the digital step function is arriving at the receiver side, it is seeing at this termination is 50 ohm. In order to achieve that, this voltage source input impedance should be, VTT should be 0. So inside your chip, if you are designing your power supply input impedance should be 0. Otherwise, it will be deflected. This is when people are deriving this type of circuit, they are assuming that power supply input circuit is 0, input impedance is 0. But it is not. In actual power supply circuit inside the chip, usually there is voltage regulator or off-chip voltage regulator. Their input impedance, this is very difficult condition. This is gonna be our class subject after the midterm exam. In your conventional circuit class, you are assuming that power supply impedance is 0. If your power supply impedance is not 0, when you are supplying the current, you're gonna suffer some voltage drop. That is there are a lot of issues associated with ideal circuit and real circuit. Anyway, we attach this termination to the VTT. Because of that, your voltage level at the receiver will switch from low level to high level and high level to low level. And we're gonna have reference voltage Vref. If your voltage is below reference voltage, this is digital logic level low. If your voltage is higher, you're gonna have a digital logic level high. You have some reference voltage here, and signal line will go up and down across this voltage reference. You know, this is usually common mode. And you're gonna switch between the low level and high level across this reference. In CMOS input, you have to determine whether it is a logically low or high level. And you determine that is the half voltage of 2.5 volt. And this is becoming this reference. In order to have this common mode, we need to have certain common mode. That's why we put this termination impedance attached to the power supply 1.25 volts. Let me move on continuously. we are assuming that this receiver impedance is 50 ohm and source impedance is 25 ohm and transistor impedance is 25 ohm. Then source reflection coefficient is 0 and load reflection coefficient is 0. Then when this transistor is turned on, this source impedance is 50 ohm. Okay. I'm assuming that there's 0 ohm. Source impedance is 25 ohm. Then when this transistor is on, this impedance is 25 ohm. This is 50 ohm. Here we have 2.5 volt and 1.25 volt. At the steady state of high level, we can apply the circuit theory. So we have 2.5 volt and 1.5 volt, and the voltage difference will be determined by the ohms voltage division of 25 ohm and 50 ohm. And we're gonna see that it is 1.25 volt plus 0.833 volt. So this is higher level, 1.25 minus 0.833. Low level can be calculated when we are turning on this transistor. So we can calculate this voltage level here by dividing 1.25 volt with the 50 ohm impedance and 25 ohm impedance. That is going to be 1.25 volt minus 0.833 volt. So we're going to have a higher level. VH is here we have V low level here and we have V reference level here. When we are switching this transistor, we're going to generate this amount and it will be propagating along the transmission line. And this is, yes. So because of that, we are having low level voltage level and high level voltage level, and it is alternating. And we're gonna have some time delay between the source and receiver that is controlled by flight time. This is a little bit difficult. Seongguk, would you summarize a little bit? Seongguk, would you summarize a little bit because class time is almost near the end, so I'm speaking a little bit fast. Would you summarize this?
네, 교수님 잘 들리십니까?
예.
네, 일반적으로 터미네이션 방법은 리플렉션을 줄이기 위해서 사용하는 방법인데 이렇게 터미네이션에 VTT라는 새로운 파워 서플라이를 함께 물리게 되면 이제 레퍼런스 볼티지를 기준으로 하이와 로우를 정의를 할 수 있고
그렇습니다.
이를 통해서 데이터 0인지 1인지 판단을 할 수 있다라고 말씀을 해주셨습니다.
맞습니다. 그래서 근데 이제 이렇게 하는 데서 가장 어려운 점 하나는 여기가 소스 터미널, 로드 터미널에서 55을 붙였는데 이쪽에 파워 서플라이가 있지 않을 건 아니에요. 여기 임피던스가 제로가 돼야 되는 조건을 갖고 있어야 된다는 게 이제 하나의 조건이에요. 아까 캐패시터 같은 게 이제 그런 역할을 해주는데 실제로 이런 건 세상에 존재를 하지 않아요. 왜냐면 배터리 자체가 와이어를 갖고 있고 캐패시터를 갖고 있어서 그렇습니다. 볼테이지 레귤레이터를 사용한다면 다 필터링 캐패시터를 붙여요. 이제 그런 복잡한 이슈가 계속 끊임없이 이루어지고요. 이게 만약에 플레인을 통과한다 그러면 플레인 레조넌스 때문에 막 하이 임피던스, 로 임피던스 막 왔다 갔다 해요. 어디다가 막 연결하냐에 따라서 막 어쨌거나 이렇게 한 이유는 레퍼런스를 중간으로 올라갔다 내려갔다. 근데 여기서 반사 현상이 없는 이유는 여기 55옴을 붙였기 때문에 반사 현상이 없어요. 그렇지만 타임 딜레이는 생기는 거죠. 여기와 여기 사이에. 이렇게 또 하는 스킴이 있습니다. 그래서 아까 아주 기본 원리는 했지만 이게 어디에 터미네이션을 붙이냐. 여기서도 뭐 25옴, 55옴 했는데 이걸 꼭 그렇게 하라는 법 없어요. 뭐 이쪽을 오픈 시켜놓고 이쪽에 어떻게 터미네이션 시킬 수도 있고 그런 베리에이션이 굉장히 많다. 그리고 이거에 또 문제가 레퍼런스 전압이 있어야 되는데 이 레퍼런스 전압이 일정 전압 소스라는 게 세상에 또 존재하지 않아요. 이게 또 노이즈를 타서 이렇게 되면 이거 어떻게 해요? 기준점이 흔들리잖아요. 이 기준점이 흔들리면 어떻게 할 거예요? 그래서 다음 주에 하는 디퍼런셜 시그널라이즈. 남한테 리퍼를 하지 않고 같이 두 개의 시그널 가면서 서로 비교하면서 가는 또 이런 스킴을 가게 돼요. 자, 여기서는 55옴을 선택을 했는데 또 스터디 해보면 뭐 마음대로 할 수 있어요. 그걸 또 25옴으로 이렇게 또 바꿀 수도 있어요. 25옴으로 바꾸면 어떻게 되느냐? 여기서 또 반사가 일어나요. 마이너스 계수가 마이너스 reflection coefficient. If we assume that we have some impedance, in this case, source impedance 45 ohms, so we're gonna have little bit deflections, but still minus reflections. So minus reflection, minus reflections. And in this case, so we got at each transitions, we're gonna have some nippers because of this kind of things. But advantage of this one is that I'm in the initial case, I think as I remember, termination impedance was I think 50 ohm. Here termination impedance is 50 ohm. In this case, I'm assuming termination impedance 25 ohm. So we can have different combinations, but by having this will cause deflections. That is our penalty. In this case, we are not going to have, only we have time delay of TF. But in this case, we're gonna have certain deflections. But advantage of here is that when we are switching from low to high, the voltage step is just 0.892 volt. But in this case, it is 1.6 volt. It's gonna have more, it is gonna have more margin, voltage margin at the receiver side, but it's gonna have more simultaneous switching noise and more power consumption. So by having different combination of terminations, we're gonna have different reference level and we're gonna have different voltage swing and different power supply noise and different power consumption. 준영, 요거 약간 summarize 해봐 주실래요?
네, 교수님. 그 터미네이션 저항을 설정함에 따라서 이제 하이 로직 볼티지와 로우 레벨 볼티지가 달라지는데 이제 그거에 따라서 이제 시뮬테이니어스 스위칭 노이즈랑 파워 컨섬션 마진이 이제 달라지는데 그걸 이제 저희가 조정할 수 있다고 생각했습니다.
예. 그래서 이제 파워를 줄이기 위해서 자꾸 이렇게 가는데 VDQ를 지금은 2.5V라고 하고 이제 최근에는 VDQ가 뭐 이제 less than 1V로 간다. 그럼 파워는 계속 줄이는데 마진이 자꾸 주는 거예요. 이런 리플렉션이나 뭐 어디 노이즈만 타면은 또 문제가 되고 VREF 자체가 흔들려 버리면 어떡할 거예요? 마진이 점점 줄어드는 거죠. 그래서 시그널 인테그리티와 EMI가 자꾸 중요한 엔지니어링 이슈가 됩니다. 속도는 빨라야지, 전력은 줄여야지, 그런데 하이스피드로 가야지. 이런 몇 개 충돌되는 프린시플을 우리가 만나야 된다. 그런 게 이제 어려운 점이 되겠습니다. 근데 이제 지금까지 한 거에 사실 수업 준비 많이 했는데 다 못하겠어요. 근데 이제 뭐가 문제가 있냐, 이제 우리가 싱글 앤드 트랜스미션 라인으로 해서 터미네이션 하고 온갖 기법을 썼는데 이 경우는 이제 그라운드 위에 라인 하나 가는 거죠. 근데 이제 어려운 점이 뭐냐? Deflection, G0, Control, 임피던스를 일정하게 할 수가 없다. 세 번째는 노이즈, 네 번째는 아까 V 레퍼런스. 이게 다 깨끗한 이 파형이 아니라 자꾸 이게 뭐 이렇게 되니까 이런 문제가 커지니까 이걸 극복하기 위해서 생각하는 스킴이 그라운드 위에 시그널 2개를 가는 거예요. 이런 걸 이제 우리가 디퍼런셜 스킴이라고, 디퍼런셜 시그널링 스킴이라고 그러는데 요게 다음 주에 핵심 주제예요. 근데 이거는 디퍼런셜 시그널링 스킴의 페널티는 뭐냐? 와이어 개수가 2배로 늘어난다는 거예요. 우리가 GPU하고 메모리 사이에 I/O 개수를 이제 1000개에서 10,000개, 10만 개까지 늘려야 되는데 이게 곱하기 2를 만든다는 거예요. 그리고 우리가 아까 얘기한 것처럼 노이즈를 없애려면 파워, 그라운드를 잘 설계 해야 된다고 그러는데 인덕턴스를 줄여야 된다고 그랬거든요. 인덕턴스를 줄이려면 와이어 개수를 늘리는 수밖에 없어요. 그라운드 임피던스 줄이려면 와이어 개수, 인터커넥션의 개수를 줄여야 돼요. 여기서도 N개가 한 10배 늘죠. 여기서도 GPU하고 DRAM 사이에도 N개, 인터커넥션 개수가 10배에서 100배, 1000개로 100배, 1000개로 늘어나는데 여기 또 곱하기 2를 해야 돼요. 그래서 이게 또 문제가 됩니다. 너무 인생 우리 그렇게 문제되진 않아요. 뭐 그냥 대충 살면 되는데 엔지니어링적으로는 이런 문제가 되는데 제가 생각하기에 이런 문제가 10년에서 30년 갈 것 같아요. 한 100년? 그래서 여러분들이 전공을 하더라도 제가 여러분 전공이 원래 있다. 아날로그 서킷 디자인 한다. 뭐 패키지를 한다. 이렇게 하는 그 중간 영역에 인터커넥션을 잘 알고 EMI를 알고 여기다가 AI까지 이해하고 그러면 3억짜리 연봉은 뭐 된다. 이렇게. 돈이 전부는 아니고요. 이왕이면 그래도 연봉 많이. 자, 여기 오늘 강의 마치겠습니다. 다음 주 또 재밌게 해볼게요. 근데 하고 싶은 얘기는 너무너무 많은데 시간은 제약돼 있고 영어고 줌이라는 이런 한계가 있는데 그래도 제 열정을 이해해 주시면 좋겠습니다. 여러분 감사드리고요. 다음 주에는 더 재밌게 해보겠습니다. 생각보다 이것보다 더 재밌을 것 같아요. 왜 디퍼런셜로 해야 되나? 근데 따지고 보면 디퍼런셜 해봐야 곱하기 2예요. 근데 곱하기 100 할 때 생기는 문제가 크로스톡. 노이즈 문제는 파워 그라운드. 이게 우리 클래스 전체 한 학기 수업 내용이라 이렇게 보시면 되겠습니다. 다음 시간에도 또 세현이, 태호, 동열이, 서보경, 조세영 이런 학생들께 또 질문 드리겠습니다. 여러분 안녕히 계십시오.